Hello. Welcome back to Learn It from a Layman. I'm Carl Christensen. I have here Cameron Christensen and Matt Christensen again. We are here today to discuss the very lay subject of orbital mechanics, or for you laymen, rocket science. So, once again, really treading in some pretty deep waters in which I do not belong. But we are going to do our best here, and we have Matt, who has, as you may have noticed from our previous podcast, significantly more physics and math experience than Cameron or I do. But Matt's going to walk us through a little bit about orbital mechanics and start with, I think, explaining a little bit about orbits in general. So, Matt, do you want to take this so I don't bungle it?
Okay, sure. So, a couple things. One, what is an orbit? Orbits have meant different things to different people throughout the years. It is, back in the 90s, it was a disgusting type of drink that had little floaty bits in it that people used to love for some reason. Now it's a type of gum, I think. But through the ages, orbit has meant the rotation of something around something else in a regular and stable pattern. And so when we talk about orbital mechanics and space orbits, we're talking about the motion of some object around some other celestial object.
Hey, quick question before you dive into like the science of it. Do you know any like the history? I know like Copernicus and all that kind of stuff. The whole idea that they're the Earth-centric universe. At what point did the idea of us orbiting someone else, or the idea of space orbits, start coming into the general scientific community?
Well, I don't know. I mean, it's been, our understanding has become more clear over the millennia, but way back, people figured out that something was moving around something else just because the night sky would change and the sun didn't appear to stay in the same spot. It moved. And a lot of initial thought was that, well, the sun zips around the Earth. That makes sense. And then a bunch of special individuals came around in the last few years and said, no, the Earth is flat and the sun is totally in a different reference frame, but we don't acknowledge those people. Our correct understanding of orbital mechanics really came about with a very smart dude named Johannes Kepler. And I'm trying to remember exactly when he lived. I think he was in the 1600s. But he is the guy that kind of defined the real true equations for orbital motion. And he, all of these scientists, they come out with their laws in groups of three. So Newton had his 3 laws of motion. Kepler had his 3 laws of orbital motion. And I guess he was right around the same time of Newton, in the 1600s or something, maybe. I don't actually know. But
must have been something in the water then.
Yeah. Right around then, you had people getting correct ideas about what moved around what. The Earth moves around the sun instead of the sun moving around the Earth. But Kepler is credited as the first guy to really define the equations that establish orbital motion. And then there's some question: was it really Kepler? Was it his assistant Tycho Brahe, or all these other things?
Kepler or some other man? Kepler or some other man by the same name?
Yes, yeah, one of those guys. So
okay, so you were going to say the laws, Kepler's laws?
Yeah. So really quick, when we talk about orbits and all of that, there's a couple of things to keep in mind. And one of the best examples of how to think of an orbit is if you can imagine yourself as a supervillain, because who hasn't done that? And you have your volcano lair. And at the top of your volcano lair, you have built your giant doomsday cannon. So it's elevated above sea level at the top of this volcano. And you load your cannon up with your doomsday device, and you fire it horizontal to the ground. Well, your doomsday shot is going to zip out of the cannon and go at a trajectory horizontal to the ground until gravity pulls it down. Well, gravity is always pulling it down until the force of gravity brings it down into the ground. And at that point, it's going to hit the city that you've targeted and annihilate it. And you will keep doing that until the governments of the world pay your bazillion-dollar ransom. Okay, so
this sounds terroristic.
Whatever. The big thing is, as you're a supervillain and you're thinking about this, you need to be able to target all of the cities that you need to hit in order to get your ransom paid. So the first city is pretty close to you, so you fire your shot, again, straight horizontal to the ground, because you don't mess around with ballistics, and you load it up with enough powder to carry the shot there by the time that gravity pulls it down to the surface of the Earth. Well, the next city is further away, and so you load up more powder to increase the range. Your shot is still going to fall at the same rate, but because you've given it more horizontal velocity, the shell goes farther before it hits the ground, and it obliterates city number 2. City number 3 is farther still, so you load it up with more powder, you increase the energy, the shell moves away faster, and it goes even farther before it falls and hits the ground. Now here's the thing. The curvature of the Earth is such that for every 8 kilometers you travel horizontally, you essentially move down, if you will, 5 meters. So if I fire my shell at a city that is 16 kilometers away, it not only drops the vertical distance between the top of my volcano and the base of my volcano at sea level, but it drops an additional 10 meters due to the curvature of the Earth. Now, what if I load up my cannon with enough powder such that it moves so fast that by the time it falls the distance to the ground, the Earth has curved away an equal distance? At that point, would my shell ever hit the ground?
No.
No, it wouldn't. It would be in an orbit. And that's what an orbit is. An object is in orbit if it is able to move at a fast enough speed that essentially the ground falls away below it at the same rate that it falls toward the ground. So, and this is kind of a key thing. If you ever talk about a spacecraft flying, or a satellite flying around, or an X-wing starfighter flying around, the person saying that is lying, and you should punch them in the throat, because spacecraft do not fly; they fall.
This is incredibly violent podcast.
Well, hey, you're a supervillain. You're not going to suffer fools gladly here. So things in orbit are not flying; they are constantly falling, and the rate of their fall determines their orbit.
Okay, I might be jumping the gun here, but as you get higher away from the Earth, the rate at which you fall is going to change, right? So
very much so, yes.
So the higher you go, the less quickly you need to move in order to remain in orbit, right?
Yes, and that is a perfect segue into Kepler's laws of orbital motion. So he figured out that orbits were a thing, and he really wanted to quantify things like how fast you need to go at different altitudes, and what are the laws that govern a general shape of an orbit? Can I have an orbit that is a triangle? He quickly determined, no, you can't. But his 3 laws, and these apply to any situation where you have really only 2 objects. So, for example, the Earth and the Moon, or the Earth and a satellite, or the Sun and the Earth. Any system where you have 2 objects like that, one orbiting the other, will obey Kepler's 3 laws of orbital motion. And the first law is that your orbital shape is going to be an ellipse. Not quite a circle, but an ellipse. And that is what your satellite will move around in. Your second law is, also the central point, or the kind of reference point for that orbit, that the satellite will orbit around, is going to be at the focus point of one of those ellipses. And you can tune into our podcast, An Introduction to Geometry, which we will definitely do at some point probably, to learn more about ellipses and their focus points. But if you look at any satellite that's orbiting the Earth is at one of the focus points of that orbital ellipse. The second law is complex and talks about how as a satellite moves around that elliptical track, if you draw a line between the satellite and the center point, the Earth or whatever it is, that line will sweep out an equal area for any equal intervals of time. Okay, that's neat sounding, but what it actually means is that the speed of the orbiting satellite varies depending on where it is in the ellipse. And what you have are two concepts, apogee and perigee. Apogee is the point in the ellipse that is furthest from your central point, the Earth, and perigee would be the point where a satellite is closest to the Earth. I'm just going to use the Earth satellite system. This could also be Earth Sun or Moon Earth or whatever, but I'm just going to say Earth satellite. If you think of a roller coaster, you go up the little track and you chug along, and you're not moving very quickly as you increase elevation toward that apex point. And then you're at the apex, you slowly start to tip over. You're still not moving fast, even though everyone is shrieking. And then you reach that point where you're on a downward slope, and suddenly the roller coaster is moving very, very, very quickly. And its speed is at its maximum when it hits the bottom of that, drop. And then the speed decreases as it goes back up the hill toward another peak point, and everyone catches their breath, and then the roller coaster is chugging along at low speed until it hits the next drop, and then you go down faster. Well, satellites are just like that. They're like a roller coaster. And that apogee point, where you're farthest from the Earth, is the point in the roller coaster where you're at that peak, and you're not moving very quick. And it's the same with a satellite. A satellite at apogee is going to be moving at slower than at any other point in its orbit. And then as it starts to come back down towards the Earth, toward that perigee point, towards that lowest point, it's going to accelerate until when it reaches perigee, it's moving at its maximum orbital speed. That's Kepler's second law. Satellites are roller coasters. That's the best way to sum it up.
So even in once it's a satellite is established an orbit, it still continues to speed up and slow down as it moves.
Yes. The exception to this is if you somehow manage to get a satellite in a perfectly circular orbit, which is next to impossible. All satellites are in some sort of elliptical orbit to some degree or other. But if you had a theoretical perfect circle, then the satellite would be moving at a constant speed throughout, because you don't have an apogee and you don't have a perigee. You're at the same distance from Earth no matter where you are in that circle. But if you have any degree of ellipsiness, that's a horrible word, and I'll use the correct word later, then you're going to have an apogee point where you're moving slowest and a perigee point where you're moving fastest.
So that's true about the planets then too.
Very much so. All of the planets are in slightly elliptical orbits. Weirdly, when the northern hemisphere has its summer, we're actually closer to apogee as regards the sun. We're farther from the sun than we are in the winter. A little bit strange. The reason that the winter is still cold is because of the orbital tilt rather than our actual distance to the sun.
Got it.
So anyway, that was Kepler's second law. Kepler's third law is more of the quantification of speed as relates to the geometry of the orbit. And you actually hit this earlier. If you're at a low altitude, you need to be going much faster in order to maintain a stable orbit. If you're at a high altitude, because of the changes in gravity and the forces that are on you, you're actually moving much slower. And there is a specific equation for that. For those of you interested, it is your circular velocity is equal to the square root of a constant g times the mass of the Earth divided by the essentially the orbital radius, the distance between the satellite and the center of the Earth. That's cool. You can look up that formula. Nobody cares. But what it really means is that a satellite way clear out there in a distant orbit is going to be moving at a much slower speed than a satellite like the International Space Station that is relatively close to the Earth and is zipping along pretty quickly.
Hey, I gotta actually before we move on here, a quick teaser. So I know some people might be tuning in shortly after, or listening to this podcast shortly after having seen the SpaceX launch. So we're going to talk a little bit about orbits and launch here at the end of the podcast. So if you're interested how that works, stick around. And then we have another podcast first at the end of this podcast as well. Sorry. Okay, so we'll jump back in. You were saying, Matt.
Well, that was it. That was Kepler's
that was it.
laws
right,
there.
Exactly.
Yep. Now you know orbital mechanics. Any questions? Go and be rocket scientists.
Yes. I do actually have, I don't know if this fits in this, in Kepler's the 3 laws, but so let's start with the moon, I guess. So the moon is orbiting around the Earth, which is orbiting around the sun, right?
Yes. Last anyone actually verified, that was still the case.
Well, good. I am a rocket scientist, I believe now. So
excellent.
The ellipsis that is defined by the orbit around the Earth is also influenced by the orbit around the sun, though, right? Like the Earth as it travels around the sun, the moon as it travels around the Earth, that ellipsis has to be affected by the gravitational pull of the sun, too, right?
It very much does. And we can jump into that when we talk about orbital perturbations, which we can totally do right now if you'd like.
Sure.
All right. So as I mentioned, there's no the satellites are all in ellipses. You can't get a perfect circle. And in fact, you can't get a perfect ellipse either because there are perturbations in your orbit and things change. And actually, before we talk about perturbations, let's talk about the 6 classical orbital elements that are used to define and measure an orbit. In order, they are the semi-major axis. This is essentially the length of your ellipse, or rather half the length of your ellipse. Where a circle has a radius, an ellipse will have a semi-major axis, and then a semi-minor axis. But anyway, the semi-major axis really determines how big your orbital ellipse is. The next one is the eccentricity, and this is measured on a scale of Carl to Tim, where if the eccentricity is more of a Carl, then I'm sorry.
Does that mean I'm less eccentric or more eccentric?
I will leave that to the listener's imagination. The eccentricity is valued between 0 and 1, and a 0 value means that the orbit is a perfect circle. Again, that's a kind of theoretical possibility more than anything else, but you can get pretty close with a circular orbit. So if you're in an effectively circular orbit, you have an eccentricity of 0. If you get up to close to 1, you're in a very, very elliptical orbit.
That's like a comet, then.
No, well, actually, yes. It's very much a comet. It's a recurring comet.
Right.
If you get greater than 1, you're in a parabola or a hyperbola, which, we have comets that do that too. It means that you're going to come down here, bend around some object in space, fly off in a different direction, and never come back. And at that point, you're not a satellite anymore. You're something else. But that is the second measure of an orbit, is the eccentricity. The third measure is the inclination, and this is just where the plane of the orbit is, how much that plane is tilted relative to the equatorial plane of the Earth. And if you think about it, you have satellites that can orbit the Earth in all different directions and in all different orientations, but they all have to cross the equator. And if you have a satellite that is orbiting essentially on the equator, then its inclination is going to be 0. And if you hold up a globe, your satellite will be zipping around the globe effectively horizontally until the end of time at its 0 inclination. Now, what if I have a satellite that I want to send over the poles instead? Well, then I need to tilt the plane of that satellite's orbit, and I can have a 90-degree inclination, 100-degree, whatever, in order to get the coverage that I want for my satellite. So that's the third element. The next three are a little bit, I'll just touch on them. There's all kinds of things you can look up to learn about these, but you have the right ascension of the ascending node, or the RAN, and this basically determines how that plane is twisted relative to a fixed point in extragalactic space. It's the orientation of that plane in terms of its twist, not its inclination, but if you were to rotate the orbit around the Earth, if that makes any sense, you would have different right ascensions of the ascending node. This is hard to illustrate verbally. It goes much better with a globe and a hula hoop. But anyway,
that's when we get that's when we get our own TV show.
Right.
So we can.
So the fifth one is the argument of perigee, and this is kind of if you think of the RAN as twist, I'm not sure what you would call the argument of perigee, maybe tilt or something, but this is where the perigee point is in relation to the right ascension of the ascending node. It's measured in degrees, 0 to 360. And then the final one is true anomaly, which has to do with where the satellite is at a given moment in time relative to its perigee point, again measured in degrees, 0 to 360. So with that, you have your 6 orbital elements that define the shape of the ellipse that your satellite is in. You have its semi-major axis, how big it is, eccentricity, how elliptical it is, inclination, how much it's inclined relative to the equatorial plane, the right ascension of the ascending node, how much it's twisted around the globe, argument of perigee, where is the perigee point, and true anomaly, where is my satellite right now. With that, all of that can be shifted and tilted and warped and distorted by different perturbations that you get in the space environment. The big one that we deal with is drag, because believe it or not, there is air in space and other junk in space, and all of that stuff slows a satellite down. It really comes into play at lower orbital altitudes, between below about 1,000 kilometers is where you really see significant drag. But over time, that becomes enough to distort your orbit, and really what you see is your orbit shrinking due to drag. The other one that is kind of interesting is called the J2 effect. And this has to do with the fact that the Earth is not perfectly round. Ha! Who knew? Rather, it's not perfectly spherical. I should be careful with my language. If you think of the Earth as a basketball, that's kind of, it's wrong. What you need to do is think about the Earth as a basketball with a fairly large dude sitting on it. And when he does that, the basketball is going to bulge out around the middle, right? Yes, totally
yes.
will. Well, that's actually what the Earth is shaped like, a squashed basketball. And at the equator, the radius of the Earth is much larger than it is if you were to measure it from the center of the Earth to one of the poles. Because of that, the Earth, and because the Earth is not a uniform oblate spheroid, there are areas of greater and lower density. Earth's gravitational field is not completely constant, and so that will also warp a satellite's orbit over time. And then the final thing that you kind of alluded to earlier is the fact that Keplerian laws apply in a two-body system, but there is no two-body system. Everything is a multi-body system. All of the satellites orbiting Earth are affected to some extent by the gravity of the Moon, the Sun, Jupiter, random comets, the invading Death Star, all of those things.
Wait, that happened?
Oh, pretty sure.
Dang it.
Yeah, everything in space applies a force to everything else in space. Back in our physics podcast, I mentioned this when I talked about the gravity equation. And, to clarify, in that podcast, I actually stated it incorrectly. I'm sorry. I will state it correctly now. The force of gravity between any two objects in the entire universe is equal to a constant g times the product of the two masses. And last time I said sum. I am sorry about that.
That explains everything.
No, it doesn't. I mean, yes, it does. Yeah. Anyway, it's g times the product of the two masses, Earth and a satellite, or Earth and the sun, or the moon and the sun, whatever it is, divided by the distance between them squared. But that force exists between all the objects in the universe, and it's pretty insignificant for a standard satellite orbiting the Earth when you're looking at the effect that the sun or the moon would have on that satellite's orbit. But it's still there, and over time it can lead to changes in the satellite's motion or distortions in its orbit. And so all of those things have to be accounted for by people that have very large textbooks on their desks with very complex mathematical formulas. But that's just something to be aware of when you're designing your next space mission. So, anyway, any questions on the basic orbital measures or perturbations or so forth?
I have a question. Yes.
Sure.
Okay, so you mentioned drag and other
Yes.
things that you run into. So, like you said, the higher you go, the less drag there is. I'd imagine once you get far enough away, the only drag really is, space is a near vacuum, right? So there's not air drag. So drag has to be these other perturbations, like the gravity from other.
No, drag is air drag.
So even
to
even at
about 1,000 kilometers, it's
Okay.
significant. Past that, it's still there. You still have free particles roaming around.
So even
not-
at
Sorry,
like
go
a moon orbit.
Yeah, there would still be some level of atomic material floating around in that void that would impact a moving body.
Okay.
The amount of impact would be so minuscule that it wouldn't really have too much of an effect on that body in any reasonable measure of time. So, for example, our communications satellites that we have that are orbiting Earth at an altitude of 36,000 kilometers, they're encountering some level of drag, but it's so minuscule that those satellites will stay in relatively stable orbits for millennia without interference. As opposed to down towards the Earth, the International Space Station has to burn its thrusters, routinely in order to not be slowed down to the point where its orbit would decay and it would pile into the Earth in a flaming mass of sadness and shattered dreams.
Oh, okay. So I have a question then. So the moon is experiencing drag, right? The moon itself.
Sure. A infinitesimally small amount, yes. So is the Earth as we orbit the sun.
Right. But so is there any point at which we could take the math far enough out that we could find out when the Earth is going to crash into, or the moon is going to crash into the Earth because its orbit's going to collapse?
Yeah, somebody could figure that out. And, no orbit in the universe is going to be entirely stable, I don't think. Maybe, who knows? Okay. But here we're going, way into the deep magic. And when you're talking about lunar orbital decay, you're talking far more years than we have any reason to worry about. I think the sun is going to probably burn out and consume the Earth before that happens.
Okay, good. Well, good. Then we've
Cameron's
averted
timeline of the universe. Yeah.
Right, from the thermodynamics podcast, if you want to go back. So we don't have to put that one on your to-do list.
Right. Yeah, I wouldn't worry about that. But no, orbital drag, and it really is air. It's just thin air, but it really is significant up to about 1,000 kilometers. So
Okay. Okay, one other question then. And you said it's like the sixth one you said, where knowing where the satellite is.
yes, the true anomaly.
True anomaly. Okay. So at any point there you need so if I launch a satellite into space, at any point I should be able to calculate exactly where that satellite is.
Yeah.
Not just from observation, but actually from mathematically, like walking through the orbit.
Yes, if you have, well, yes, depending on how well you account for perturbations, yeah, you should be able to get pretty close. And in fact, the government and the offices that the government employs to track stuff, when they look for a satellite, they have their little computers that chew on all these orbital elements, and they have all of those orbital equations to account for perturbations and so forth. And they can, if they're told to go look at a satellite, then they can do that because they know in general about where to point a telescope based on the math that they've done. And they can say the satellite, based on the orbit that we know it has, should be coming over the horizon at around this point, and therefore we can cue our telescope to look at it. And then based on that fresh observation, they can refresh the orbital equations and get some correct data and all of that. That's handy when you want to keep track of the ISS or whatever.
Right.
Make sure that it's still there and not decaying faster than normal.
Okay, so I have a bunch of other questions actually too, kind of along these lines, but I don't mean to derail what other structure you had. So, do you want to continue and I can come back to my questions, or how do you want to do?
Yeah, go ahead with whatever questions you got.
Okay, so when you launch a satellite, do you know approximately how long it's going to be in orbit before it needs to be brought down because its thrusters can't keep it in orbit anymore, or like what is a life cycle, what timeline of different satellites?
Yes, short answer is yes, you do know that. And responsible spacefaring nations, meaning the United States, any party to the European Space Agency, and Russia, are generally pretty good about being aware of that type of consideration and constraint. And so you would anticipate that your satellite, with whatever orbit you're going to put it in, is going to experience a different amount of drag, a different amount of influence from the J2 effect, the squashed basketball effect, a different amount of influence from the moon, the sun, Jupiter. And all of that is going to require you to expend so much fuel per year to keep your orbit corrected. And based on that, you can build a design life. And as you reach the end of that design life, again, those responsible spacefaring nations are going to either deorbit their satellite, intentionally slow it down to the point where it piles back into Earth, or in some cases, they'll move it to a disposal orbit or a graveyard orbit. For the communication satellites that we have way out there, there is a disposal orbit that is a few hundred kilometers higher than that comms orbit, and there's a bunch of junk parked out there. But yeah, you can definitely calculate your design life based on what your expected fuel needs are going to be in order to maintain your orbit.
Okay, so and you just mentioned one other thing, and this has come up in podcasts in the past, but people may have seen the movie Gravity.
Oh yeah,
right.
It's a treatise.
So moving from orbit to orbit is not a trivial thing, right?
No, and there's different parts of that. Remember those orbital elements. Changing those orbital elements requires different amounts of energy. It turns out if I want to make my orbit bigger and I want my ellipse to expand, that's pretty easy. That's just a inline thrust burn, or rather, well, it's actually at a tangent to the orbit, but who cares? That's just firing myself forward effectively, and my orbit gets bigger. And I'll come back to that because there's some nuances there. Now, if I want to change the plane of my orbit, though, if I'm inclined at 15 degrees relative to the Earth's equator, and I really want to be inclined at 19 degrees, turns out that takes a phenomenal amount of fuel. So much fuel that even the space shuttles would not do plane change maneuvers just because of the amount of energy that you need to expend to do that. So if you have two satellites or two objects in space and you really want them to rendezvous with each other, say you have a Dragon capsule carrying George Clooney and you have a Chinese space station or something, because the last one got exploded. If those two objects are not in the same orbital plane, you're well, you can do a rendezvous, but it's going to be a significant kinetic event. You won't be able to just snuggle up to it. You're going to smack into it really hard, and die. But yeah, in order to do that kind of thing, you need to be in the same plane, and in order to be in the same plane, you need to have been put in that plane to start. It is very, very difficult to change the plane of your orbit once you're on orbit.
Okay, so that just blew up that whole movie.
Kind of totally did. Yeah.
Okay, so go back and watch the movie Gravity, and then you can see it as a comedy more than a sci-fi.
Yep. There's one other point with that I want to get to. Say I'm in the same plane as an object that I want to rendezvous with. I'm in my little capsule. I'm Sandra Bullock now, and the ISS is in the same plane as me, but it's way ahead of me in the orbit. If I accelerate, I am not going to catch up to the ISS because I cannot accelerate in that same orbital track. Turns out an orbital track has a very set it has a very set speed for wherever you are in that orbital track. And if you speed up or slow down, you're not in the same orbit anymore. And so I cannot pursue the ISS along its circle or along its ellipse. If I accelerate, I'm going to make a different ellipse. And it turns out I'm going to drift way off into space, and the ISS is going to cruise by below me. The way that you actually do this maneuver is you change your ellipse appropriately so that, and you usually do it twice, so that you can come together at a later point. But you can't just chase something down alongside its same orbital track, if that makes any sense.
It does, yes. Well, I mean, I thought it made a lot of sense during the movie too, but what you said also makes sense. So I'll just have to believe both at the same time.
All right.
Paradox. Okay, so another question of mine is space junk. There's a lot. You mentioned like a graveyard for satellites. I know that space and even orbiting Earth is a big place, but there are a lot of satellites. The space age started 60 years ago or whatever. A lot of stuff up there. What are we? I mean, how often do you run into this question of space junk, things potentially hitting your satellite, and what would be the consequences of that?
Well, the consequences are really bad. So the first thing to keep in mind is that space is large. Like really large, like impossibly large. You cannot fathom how much cubic volume there is up in space. And the chances of two objects running into each other are absolutely minuscule. That said, it totally happened. Back in 2010, I think, a Russian satellite of some sort ran into, I think it was a commercial Iridium communications satellite. They smacked right into each other, and overnight, the the amount of space garbage almost doubled, just because the two satellites shattered into a million little bullet-sized pieces, each one of which could cause another catastrophic reaction with something else. Nothing's happened because, again, space is unfathomably large, but that chance is always there, and statistically, it will happen again. The likelihood on a given day of two objects colliding is measured in, tens of thousandths of a chance, but it's always there. You hear occasionally about nations doing tests to knock out satellites, and the junk that type of thing creates is also a massive problem. It's something that we don't. It's so bad for everything because of, essentially, if you have that junk. Now, keep in mind, orbits don't change normally, and so if you have junk in an orbit, it's going to stay in a predictable orbital band. It's not going to float around like some kind of planetary terrorist directly targeting George Clooney. It's going to be in a predictable orbital slot. What it means is that if you have junk floating around in that slot because of collision, then that slot is perhaps unusable for everything else. But it's going to orbit in a predictable manner, and you can easily avoid that by selecting different altitudes, selecting different inclinations, or RAN, or whatever. And so you can very easily get around this if you're, responsible, capable, and have a little more space experience than, say,
Right.
North Korea or any of those other fledgling wannabe space nations. Sorry.
You're killing our North Korean listener base.
Well, I don't really want them. Actually,
Oh, right.
I do want them listening to this, because if they're going to get scientific knowledge, then learn it from a layman is definitely the place for the North Koreans to pick that up.
Yeah, exactly. So. Better get it somewhere. Yeah. Okay, so, and you've kind of already started touching on this, but I'd imagine that the U.S. kind of tracks, obviously, the governmental satellites that are up, maybe even the now that the public sector is finally, the private sector is finally getting in, like obviously SpaceX, as we're going to talk soon about the launch, starting to launch satellites or whatever. But every developed nation can launch its own satellites. Do we track all satellites that are up there, or is there like an international body that wherewith you register your satellite? Is that a thing?
To answer your question, kind of. The U.S. does try to track all of the stuff that is in there, including all the junk. And there is a satellite catalog that includes not just satellites, but whatever's floating around up there. And we do try to, the U.S. does try to keep tabs on what's where. But again, space is phenomenally big, so there's only so much that anyone can watch at a time. The big thing that people are concerned with is safety of flight for especially manned space missions. So you can bet that the community as a whole is tracking things in low Earth orbit near the International Space Station, and that they would want to be aware if anything is looking like it might come within a dangerous distance towards the ISS.
Okay. So there's no international body though that records these things. It's each nation. It's incumbent on them or whoever's putting the mission together, launching the satellite, to figure out, okay, this might be what I need to take into consideration.
Yeah, as far as I know, I don't know. Maybe the UN has some kind of space body. There's the European nations, as I mentioned, have the European Space Agency, the ESA, and they all contribute to that kind of European consortium.
Okay. Okay. That's the questions I had for now. Do you have other things you want to talk before we touch on the launch?
Yeah, let's talk about types of orbits and where they are and what you would do with them. There's 4 basic orbital types. There is low Earth orbit, which is defined as, well, it's kind of ill-defined, but it's roughly everything that is, 1,500, 2,000 kilometers or lower. therefore low to the Earth. Past that point, you start to run into the Van Allen radiation belts, which is just this big cosmic donut of high energy radiation that gives satellites diseases and kills them. Within that giant donut, you have medium Earth orbit, or MEO. And about the only things that we have up there are the GPS constellation and really all of the other foreign imitations of GPS, Russian GLONASS, European Galileo, things like that. Those are all sitting up there in medium Earth orbit. And those satellites have a large amount of radiation shielding on them so that they don't just die from all that Van Allen radiation exposure. Past that, you have a very special orbit called geosynchronous orbit. And that is at an altitude of about 36,000 kilometers. And it's the altitude where the satellite orbits the Earth at a rate of 1 orbit per day, which conveniently means that that satellite will essentially stay parked over the same point on the Earth forever. That is massively handy if you want to put a communications satellite up there, because you can aim your little satellite dish at that orbiting satellite, which will stay overhead until the end of time or until the perturbations move it. And you can relay signals very reliably and very easily. And that's the third orbit. It's chiefly communications satellites up at geosynchronous orbit, or GEO. And then the fourth orbit is the highly inclined orbits, or highly elliptical orbits, rather. I'm sorry, HEO. And these are massive elliptical orbits where the perigee close to the Earth is on the order of 1,000 or so kilometers, and then the apogee is clear out at 40,000 kilometers or something ridiculous like that. And these are used for communications at essentially near the poles. Satellites in geosynchronous orbits are great for comms, but they don't do so well at high latitudes up near the polar regions, just because the signals don't get through the same way. And so if you put a satellite in an inclined and super elliptical orbit, then you can have a reliable extended communications coverage over those polar regions. The Russians and the Soviets before them made extensive use of highly elliptical orbits because Russia happens to be at pretty close to the pole. And so their communications needs were not always able to be met by geosynchronous orbiting satellites. Within that, you have all these different things at these different orbits. I mentioned GEO is used mostly for comms. Highly elliptical orbits, same things. MEO is used for navigation and timing satellites like GPS. And then low Earth orbit is used for everything else. This is where you have your science experiments. This is, in general, if you want to do imaging of the Earth, you want your camera to be close so that it can get high resolution. So your Google Earth satellites are all going to be down in low Earth orbit, snapping away the pictures of your whatever.
So at night, you can see satellites sometimes moving along above you if you look closely up into the sky, right?
Yeah.
Are those your low Earth orbit satellites, or which ones are those?
Yeah, okay. Those would be anything in low Earth orbit. Anything farther than that, I mean, these satellites are not super large. Some of our largest communication satellites out in geosynchronous orbit are about the size of a bus. Now, imagine looking at a bus 36,000 kilometers away. It's going to be a little bit difficult to see, yeah. That said, even looking up into low Earth orbit to see a minivan that is 500 kilometers away, that's a stretch. But occasionally, that minivan will be picking up the glint of reflected sunlight in just such a way that, yeah, you could see it in the night sky. You can often see the ISS is only at about 200 and something kilometers. It's pretty low. And you can often see that in the night sky, depending on how it's illuminated.
Cool.
But that's what the different orbits are, and that's what you would use them for. If you want to take pictures close to the Earth, if you want to do all of our weather satellites, those are generally in low Earth orbit because you're sensing something on the Earth. Higher orbits are for comms and other different things. So,
Okay.
anyway, those are that.
Nice. Okay. Were there anything else you wanted to cover before we talk launch?
No, let's talk launch.
Okay, so this is something that I think most of the lay audience, to which we try to appeal with the name of Learn It from a Layman, has a lot of, the intrigue in is, the launch, essentially the blowing up of something and the potential for lots of things to go wrong. And so as today, there was a successful launch of a manned shuttle, right? A manned mission for the first time in a long time from the United States, at least. What do you have to take into consideration when launching a satellite or a shuttle into orbit? And obviously, those are going to be significantly shorter missions, right? So you need to know. I guess what are the additional considerations?
The big thing is just energy. If you have a heavy satellite, it's going to take more energy. If you have a high orbital altitude, it's going to take more energy. If you have a heavy satellite going to a high orbital altitude, like a giant comms bird, then that's going to take a ton of energy. And so the selection of your launch vehicle will largely be based on what are you trying to put in space and how far is it going. Past that, the other thing that comes into play is really the orbit that you want to put it in terms of its inclination. Based on geometry and math and a whole bunch of other cool stuff, the launch site that you have is really only able to launch directly into an orbit that has the same or greater inclination as its latitude above the equator. So think about this. I want to launch into an equatorial orbit. I just want my satellite to go along the equator all the time. Can I launch into that from Cape Canaveral in Florida, given that Cape Canaveral is
north
above the equator?
No.
Well, in order to do that, I have to launch south. And then once I get into that equatorial point, I have to do a plane change. And that plane change is a phenomenally expensive maneuver in terms of energy and fuel. So I can do it, but it's very, very difficult. However, if I'm down in Ecuador, I can launch straight into that equatorial orbit. Or if I have there was a company called Sea Launch. They did just that. They launched from the sea. And I think they may have even made it into an Avengers movie at one point. But basically, they put your rocket on a barge, they float it down to wherever, probably the equator, and they fire you off from there, and you go directly into an equatorial orbit at low energy cost, and it's great, and everyone's happy. Now, going back to Florida, what if I want to go into a polar orbit instead, where I'm orbiting the poles, about 90 degrees on my inclination? I can definitely launch straight into that. Just because that's easy. The geometry works in my favor there, but the rule is that the latitude of my launch site has to be less than or equal to the inclination of my orbit. The ISS, I forget what orbit the ISS is in. It's pretty inclined, but the nice thing about that is because it's so inclined, you can launch into that orbit from almost anywhere, which is a good thing. However, if the ISS were in an equatorial orbit, it would mean that you would have to launch from the equator and only the equator, and that would be pretty difficult.
How often? So that would seem to be the case that if you wanted an equatorial orbit, if there were any benefits of that, the nations that are on the equator would be I mean, you'd have to have a relationship with them in order to launch into that orbit, right?
Oh yeah, and those South American nations down on the equator, they do. I mean, space
Some
launch
business.
is a business there.
Nice.
So you do have, and the big one where you see equatorial orbits is at geosynchronous orbit. Again, that's that super high altitude one, where you want your comms bird in the same place in the sky, and so if you can put it on the equator, if you can put it perfectly on that equatorial line, then you have a special orbit called a geostationary orbit, where the satellite doesn't move at all relative to the Earth.
Cool.
Yeah, it's and that's big business for DirecTV, Dish Network, all those guys.
Got it. Okay. So today, so the SpaceX launch was supposed to happen a couple days ago, right? And then weather scratched the mission. I'd imagine wind is a big factor when you're launching a rocket, essentially. Are there other considerations when launching a satellite that you have to take into consideration weather-wise? How big of a deal is it when you've got wicked load of explosives strapped to the backside of you to go through a little extra wind?
Oh, it's kind of a deal, and it's not just. Yeah, we think of wind as not being a big deal because, we're firmly planted on the ground, and the friction between the soles of our feet and the earth prevent us from moving. When you don't have that same friction, you move a lot more in the wind. And so a rocket, even though it's hundreds of tons of power, would be significantly affected by winds aloft as it goes through kilometers and kilometers of air and atmosphere that is all moving with it. And it all depends. Yeah, in general, rockets can handle an amount of wind, but there are thresholds. The other one is back in the Apollo days. I think it was 11 or something. Anyway, one of the Apollos actually got lightning bolted on its way up.
Well,
that was no good.
Frightening.
Yeah, it wasn't 13. 13 had everything else go wrong with it. Maybe it was 15. I don't know.
So did that fry the systems? Did that
Well, it didn't make life easier for the astronauts, and they were able to recover, and they were able to get back down safely. But that's something that they very quickly realized this could be a bad thing. So let's not launch when there is lightning. Now, it turns out Cape Canaveral in Florida is inadvertently the lightning capital of the world.
Of course it is.
Yeah. So you're constantly getting weather scrubs down at the Cape because of lightning within however many miles. Those are kind of the big ones. Precipitation can cause issues, especially if you have sensitive equipment or things. Rockets are delicate, so yeah.
That's funny to say because you blast them off with loads of explosives, but I understand that obviously it matters what you plan in certain things and don't plan other things, and the unplanned things are the problems, right?
Yes, I think I agree with that statement.
Okay. Right. Okay, that was pretty much it. Any other insights into rocket science?
No, it's really pretty straightforward. So,
I think we've covered it exhaustively. So anyone that wants to contact us for a certificate, we will certainly label you a Learn It from a Layman rocket scientist for whatever that's worth. Okay, so I did tease out a podcast first here. And that is, we're going to actually announce the subject of our next podcast because, heavens, we've never been that organized before. We're going to be doing a writing podcast next, and we're going to actually invite an author to discuss writing and how to get published and what good writing is, and so look forward to that in the near future. Less physics, less orbital mechanics, but some, I'm sure. So, all right. Well, thanks, Matt. And Cameron, well, I will sign off now, and we'll sign off now, and we will see you guys back again for our next episode.